So last time we have learned the oxidation of different kind of alcohol. So if we have primary alcohol, we can oxidize it, and finally we can get it up to carboxylic acid. But if we have a secondary alcohol, then we can only oxidize it to ketone. And for tertiary alcohol, it won't have any reaction with acidified potassium dichromate. Okay, so the first one, which of the following compounds will produce a carboxylic acid? So for this one, we need to find a primary alcohol. Okay, so take a look. The first example, this is a carbon that hydroxyl group is attached, and it has 3 methyl group attached to it. So this one is a tertiary alcohol. Okay, tertiary alcohol won't have any reaction with the catalyst we use here. How about the second one? Second one, again, we find the carbon that attached to the hydroxyl group, which is this one. And then how many alkyl group is attached? So we have this one. That's the first alkyl group attached to the carbon. And here we got the other one. Okay, so this is a secondary alcohol. So for a secondary alcohol, it will only be converted into a ketone, okay, by using that catalyst. How about C? Okay, again, we do the same. Find the carbon with hydroxyl group. Okay, so in this case, you cannot find any hydroxyl group, but we can find a carbonyl group. Okay, so you can find a C double bond O group here. Okay, so this one, because it's in the middle of the carbon chain, so this molecule is a ketone. And remember, ketone cannot be further oxidized to form carboxylic acid. Only aldehyde can be oxidized to form carboxylic acid. Okay, so C is not possible. So the correct answer should be D, and we can double check that. For D, this is a carbon, okay, and remember when we write HO, that means it's an aldehyde, not an alcohol, okay? So for aldehyde, if we put the catalyst in it and doing it under a heating under reflux, then we can get carboxylic acid, okay? So that's for the first question. Second one, many alcohols are oxidized by warming with acidified potassium dichromate solution. Which of the following alcohols resist this oxidation? Okay, so for this one, we need to find the tertiary alcohol, okay, because tertiary alcohol cannot be oxidized using acidified potassium dichromate. So the first one, we have the hydroxyl group attached to this carbon, and for this carbon, it only got attached to a benzene ring here, a phenyl group. So this is a primary alcohol. Okay, so it can be oxidized by the catalyst. And for the second one, okay, this is carbon that the hydroxyl group attached to. Again, it's attached to one alkyl group here. So again, that's a primary alcohol. How about the second one? For this one, the third one. For this one, that's a carbon that hydroxyl group is attached. And for this carbon, you can see there are 3 methyl group attached to it. So this is a tertiary alcohol. And tertiary alcohol cannot be oxidized by acidified potassium dichromate. So we should choose C. And for the last one, again, we can check. This is a carbon, the hydroxyl group is attached. There are 2 alkyl group is attached to, a methyl group and ethyl group. So for this one, that's a secondary alcohol. Okay, so it can be oxidized to form ketone. Okay. So question 1 and 2 pretty straightforward. Let's come to a bit complicated question. So some reaction of butene are shown below. Okay, so let's take a look. This is a butene. It's a symmetrical molecule. So if we add hydrogen, okay, if we add hydrogen to it, then it will undergo electrophilic addition. Okay, so after electrophilic addition, we will get this molecule. So hydrogen would just be added onto both sides of the double bond. So you will get this molecule. It will undergo electrophilic addition reaction. Okay. Okay, and then take a look at B. This one, okay, again, the butene molecule is reacted with bromine, which is dissolved in organic solvent. So no water is present here, no no OH ion. Okay, so in this case, again, it will undergo electrophilic addition, and bromine, okay, will just add on both sides of the double bond. Okay, so we can draw the product. It should be CH3CHBr, and then CHBr, CH3. Okay, so for this one, again, it's electrophilic addition. Okay, so next one. This time we're adding it with hydrogen bromide. Okay, so for this one, again, it will add onto both sides of the double bond. But this case, we need to consider which side it's going to add on. But since we have a symmetrical molecule, so you can just draw either side. So the product would be CH3, CHBr, and then CH2, CH3. Okay, so again for this one, electrophilic addition. Okay, so move on to D. Okay, this time we have cold dilute potassium permanganate, and it's in acidic condition. So for this one, after the reaction, we're gonna have OH group added onto both sides of the double bond. Okay, so again, it's a reaction that we have learned in Unit 27. That's the electrophilic addition. Okay, so the product we formed should be CH3CH, and then the OH group add to both sides of the double bond. And then we have CH, OH, CH3. Okay, so the type of reaction, electrophilic addition. Okay, so now we have a diol. So we have two OH group in that molecule. And then we put it with acidified potassium dichromate, and we heat it on the reflux. So this molecule would undergo oxidation in this condition. So what's going to be the product here? So the OH group, hydroxyl group, would be oxidized to carbonyl group C double bond O first. Okay, so let's draw that product and see if further oxidation can happen. So we would have CH3, CO, and C double bond O again, and CH3. Okay, so now it become ketone. Okay, so the OH group have become a carbonyl group C double bond O. Okay, but here we have ketone. Okay, the carbonyl group is in the middle of the carbon chain, so no further oxidation would happen. It won't be further oxidized to carboxylic acid. Okay, so the reaction will just stop here. So here, this part, the reaction is just oxidation, and we'll just stop here. Okay, because it's not aldehyde, so further oxidation will not happen. Okay, so next one, which compound A to E is or are chiral? Okay, so take a look at the first one. Okay, so first one, remember to be, in order to be a chiral molecule, it has to attach to 4 different atoms or groups of atoms. But for molecule A, okay, you can see even the middle one, these 2 carbon, is attached to 2 identical hydrogen. So there's no chiral carbon in this molecule. Okay, so A is a chiral. Okay, how about B? For B here, if we focus on the middle 2 carbon, for this carbon, for example, because it's symmetrical, so for this carbon, you can see it attached to a methyl group, it attached to 1 hydrogen atom, and also attached to 1 bromine atom, and then further it has this alkyl group attached to it. So it has 4 different groups of atoms attached to this carbon. So that can be a chiral carbon. Okay, so remember we use a star to represent the chiral carbon. So again, for this one, that's a chiral carbon as well. So B can be a chiral molecule. Okay, and then take a look at C. For C, again, we need to find out whether we have a carbon that attached to 4 different groups of atoms. So if we focus on this one, it would attach to a methyl group, a hydrogen atom, a bromine atom, and then an ethyl group. Okay, so this carbon is also a chiral carbon, so we can put a star next to it. Okay, so how about this carbon? Okay, similar to this one, but here we have hydrogen added onto this side of the double bond. So for this carbon, at least you can see it has 2 identical hydrogen to it. So this carbon is a chiral this time, okay, because it's bonded to 2 identical hydrogen atoms. So no star can be put here. Okay, this is not a chiral carbon. Okay, so only the one I put the green star, this one is the chiral carbon. But for this molecule, since it has 1 chiral carbon, so again it can be a chiral molecule. Okay. Okay, so next one, if we have D, okay, this one, check is symmetrical, so we just look at one side of that molecule. Okay, so for this carbon, it got 3 identical hydrogens, so we don't consider it as a chiral carbon. The next carbon here. Okay, so this one, we have 1 hydrogen attached to it, and then we have a hydroxyl group attached to it, and then we got the methyl group, and then finally this alkyl group. So that's this carbon is attached to 4 different groups. That's a chiral center. Okay, so because it's symmetrical, this carbon should also be a chiral carbon. Okay, so for this one, again, is chiral molecule. Okay, so far we've found 3. Okay, B, C, D can all be chiral. Okay, and finally we're going to check E. So E, we have carbonyl here. Okay, so that makes it flat for that molecule. Okay, so if we have a flat molecule, then it won't be able to bond it to 4 different groups of atoms. Okay, so see this carbon, it just double bond to O, and then a methyl group, and then the alkyl group. So only 3 groups of atoms. So there's no chiral carbon on this molecule. Okay, so for part B, the answer should be B, C, D only. Okay, make sure you label the chiral carbon to remind yourself while working through all the molecules. Okay, and then the last one for this part, when compound D is heated with excess dehydrating agent, hydrocarbon F is formed. Hydrocarbon F decolorizes aqueous bromine quickly. Write the structure formula of F. Okay, take a look at D, what we have here. Okay, so D, we have the diol here. Okay, when we are heating it with dehydrating agent, we're going to remove water from that molecule. Okay, and then we're going to form the hydrocarbon F, which can decolorize aqueous bromine quickly. So alkene will be able to decolorize aqueous bromine quickly. Okay, so we are going to convert this diol into an alkene. And where to remove the water on this molecule, maybe if it's easier for you to understand if I draw the structure, the complete structure. Okay, OH group here, and then we have the other one. Okay, so here we are going to remove we are able to remove 2 hydrogen from this molecule. So the first one, we would remove this part, this hydrogen. So a double bond will be formed between these 2 carbons. And second, we can remove this set of water so that a double bond will be able to form between these 2 carbon. So the structure formula of F should be CH2 and then the double bond CH and then CH double bond to CH2. Okay, so after removing the water, so undergo dehydration, they would form the alkene. Okay, so for part C, the last part, because it's heated with excess dehydrating agent. Dehydrating agent means it's gonna take away water, and also it gives you a hint that the product would decolorize aqueous bromine quickly. So that means you will be able to get an alkene after the dehydration process. So dehydration of alcohol, we have learned. So we're gonna remove water. So we're gonna remove one of the hydrogen that next to that hydroxyl group. So in this case, because we have a diol, we will be able to remove two water molecule from that. Okay, so the first one would be this part on the left hand side. We're removing the hydroxyl group together with this hydrogen, and then we will be able to form a double bond between these 2 carbon. And on the right hand side, we're going to do the same. We'll remove the hydroxyl group together with the hydrogen next to it. So we're going to form another double bond between these 2 carbon. Okay, so that's the final product we have here, the alkene. Okay, the diene here, and we can check because of the double bond, it's gonna decolorize aqueous bromine quickly. So that's a final product. Okay. Now let's move on to the next part. Question 4. Okay, here we got a flow chart shows some reactions involving cyclopentanol and a cyclopentene. Okay, so this one we have a hydroxyl group attached to that carbon cycloalkane, and then we get an alkene with double bond, carbon-carbon double bond. Okay, so by using the dehydrating agent, so we're removing water here, and we're removing this hydroxyl group with this hydrogen. Okay, so a double bond will be formed between these two carbon. Okay, and we also have a reaction with acidified potassium dichromate and heating under reflux. And for the cyclopentane, we have a reaction that we add bromine in organosulfur. Okay, so take a look what's the question looking for. First one, describe a test to confirm the presence of the hydroxyl group in cyclopentanol. State also the expected observation. Okay, so remember we have learned the method to test the presence of the hydroxyl group. So in order to test for it, first the reaction should be easy to carry out. Okay, so hopefully we want to do it under room temperature. And second, it should have a obvious observable change. Okay, so remember the reaction we have learned before, we use a PCl5, okay, phosphorus pentachloride. Okay, and that reaction would take place at room temperature, and the expected observation is that the steamy film is produced. Okay, so the reagent we use is PCl5, and the expected observation would be a steamy film produced. Okay, so this steamy film is due to the hydrogen chloride gas, okay, the gas produced. Okay, but remember when you are writing observation, no need to don't mention the name of that compound, okay, because you haven't tested that product. Okay, so that's a test for the hydroxyl group. Part B, suggest what dehydrating agent A might be. Okay, so you got a lot of choice, but the reagent we mentioned in this unit can be a concentrated sulfuric acid or concentrated phosphoric acid. Make sure you have put the concentrated on. That condition is essential, okay? Because dilute sulfuric acid won't have any dehydrating effect on the molecule, okay? Make sure you put the concentrated sulfuric acid or concentrated phosphoric acid. Okay, and then next part, draw the structure of compound X. Okay, so for this one, we have the alcohol, and then we heat it with heated under reflux with acidified potassium dichromate. So the hydroxyl group will become a carbonyl group. Okay, so let's draw that out. So for that one, we are going to have, we draw the carbon chain first. And then the hydroxyl group will turn into a carbonyl group. So we write C double bond O here. Make sure you write the rest with hydrogen as well. Okay, so that's the structure of compound X. And since the carbonyl group here is in the middle of the carbon chain, okay, remember it will not be further oxidized to carboxylic acid. So we just stop here. Next one, cyclopentane reacts with hydrogen to give compound Y. Give the catalyst used. Okay, so that would be this reaction. Electrophilic addition, we're adding hydrogen onto both sides of the double bond. So at the, when we do the revision of that of the alkene reaction, it asks you to remember the 3 choices for the catalyst. So you can choose from nickel, platinum, and palladium. These 3, one of them. Okay. And then next part, cyclopentane reacts with bromine in organosolvent to give compound Z. Okay, it's this part. Cyclopentane reacts with bromine in organosolvent. So no water is present. Okay, no OH minus is present in this reaction. And what color change will be observed? So it will change from orange, that's the color for bromine in organosolvent, and after the reaction it will just change to colorless. Okay, the next part, draw the structure of compound Z. So what will be the structure after that? So for this one, again, it will undergo electrophilic addition. So bromine will add to both sides of the double bond. Okay, so we just need to draw that structure. Again, we draw the carbon chain first, and then we draw the bromine, which added onto both sides of the double bond. Then we fill the rest with hydrogen atoms. Okay, and then last part. Cyclopentane can be polymerized to give polycyclopentane. Draw a section of polycyclopentane to show 2 repeating units. Okay, so 2 repeating units. And here, if we look back to the original molecule cyclopentane, we have the double bond here. Remember, when we're drawing the repeating unit, we just get rid of the double bond and then we connect it to the other repeating unit to show the polymer. Okay, so we do the same for this one. We're going to remove the double bond and we're going to connect the other repeating units here. So let's draw the first repeating unit. We are going to have this one. Okay, and then remember, from the point we have the double bond, we're going to form, okay, it will be connected to the second repeating unit. Okay, so also do that. Okay, and then make sure you have draw the hydrogen as well. Run out of space. Okay. So that would be the polymer. Sorry, that should be bromine. Okay. So on the next page, we're going to discuss some of the applications in our daily life. Okay, I don't know if you had experience to make white wine or red wine at home, but it's possible to do it at home. Okay, so the materials we need is pretty simple. We just need something that can produce, that contains glucose, and then we just need to get some yeast. And then the yeast will do some reactions and then turn the glucose into alcohol. Okay, so that's what question 5 is about. Question 5 shows a setup that we can use something, okay, oops, something that contains glucose, and then we put yeast to make the reaction to take place. So we convert glucose to alcohol, okay? And this is a simple setup, and I would like to show a video that shows you how you can do this experiment at home. Okay, so here you can see that's the materials.
Sugar, yeast, and an airlock. The amount of water, sugar, and yeast that you buy and use depends on the amount of alcohol that you plan to make. Also, the water that you use should be distilled to prevent the infection of other microbial.
Okay, so now you see the materials are very simple and you just need to do a few steps. So first, you need to weigh the sugars that you use, okay? And then you're gonna dissolve the sugars in water, okay? And then, yeah, to make it all dissolve, maybe we need a little bit heat. And after that, we put it into the bottle. And then we prepare the yeast, and then okay, and then we just need to put the yeast into the bottle.
You should top off the water while you're next, using a sterilized spoon or stick, mix the suspension thoroughly.
Okay, so pay attention to this part. That's a key to make this process succeed, to make this process successful. So if you don't have this part, you won't get any alcohol. Okay, so pay attention what this setup is useful.
The final important last step is to add the airlock. Add the appropriate amount of water depending on the airlock design that you chose. The airlock lets CO2 out but doesn't let air in. This maintains an oxygenless environment for the yeast to live in. It is extremely important that the environment that the yeast is in is oxygenless, otherwise it won't produce alcohol. You could optionally monitor your alcohol fermentation by measuring the specific gravity of the sugar solution, which is useful if you're trying to obtain a target alcohol percentage. However, we're looking to try to get the most alcohol production as possible, which is going to be near the end of the fermentation. The easiest way for you to monitor this fermentation is to simply monitor the production of CO2 gas. After an hour, it should speed up to be this quick or even faster. Near the end, the CO2 production should almost stop. So for a week or two, store it somewhere dark and cool and check on it later.
Okay, so here you can see there's this gas coming out. Okay, so that confirms you have produced there is a reaction that produce gas inside your bottle, and then it's gonna be it won't be accumulated inside the bottle, otherwise the pressure gonna build up. So we need to have a setup to release the gas. Okay, so if we go back to what's wrong with my Okay, so since we only got less than a minute, I will start again and let you to join the session. Hello, hello. Can you hear me now? Okay, yes, I'll let you to join the session again. I'll give you the new code.